Ever wondered why your phone's AI hesitates when it's unsure? Like when it tries to identify a blurry photo and says, maybe. That hesitation isn't random. It's a signal from the model's internal confidence meter. Today, we're unraveling how AI learns to know what it doesn't know, and why a new technique called CAP is rewriting the rules of uncertainty in machine learning. Let's get technical. Here's the crux. Traditional AI models are like overconfident experts. They spit out predictions with zero doubt, even when they're wrong. Imagine a medical AI diagnosing a rare condition, but refusing to acknowledge it's uncertain. This is the problem we're fixing. The key lies in uncertainty quantification, the process of measuring how confident a model is in its answers. Neural networks, the engines of AI, typically model uncertainty using Gaussian distributions, those bell curves that show probabilities around an average. But here's the twist. The geometry of neural networks isn't flat. Their weight vectors, the numbers that define their learning, exist in a high-dimensional space that's more like a hypersphere than a 2D curve. Think of it as trying to measure distances on a globe with a ruler. Distortions are inevitable. Enter concentration-adapted perturbations, CAP. This method models uncertainty directly on a hypersphere, treating each weight vector as a direction, not a magnitude. Why? Because in neural networks, the direction of weights often determines behavior, while their scale can be adjusted without changing outcomes. For example, scaling a weight vector and compensating in other layers leaves the model's output unchanged. By focusing on direction, CAP captures uncertainty in a way that aligns with the network's actual structure. CAP leverages the von Mises-Fisher (VMF) distribution, a directional probability model akin to a Gaussian on a sphere. Imagine a globe where the North Pole represents the most likely direction, and the spread around it is controlled by a parameter called concentration. CAP dynamically ties this concentration to the noise injected during training, allowing each layer to learn its optimal uncertainty level. This is a departure from traditional methods that rely on post-hoc calibration, which is like adding a speed limit after a car has already crashed. The results? On benchmarks like CIFAR-10, CAP slashes calibration errors by 5.6x compared to standard approaches. Calibration here refers to how well a model's confidence matches its accuracy, so a 90% confidence prediction is actually right 90% of the time. CAP achieves this by embedding uncertainty into the learning process itself, rather than fixing it afterward. Plus, it's computationally lightweight, avoiding the heavy machinery of Bayesian neural networks or ensemble methods. But the real win: interpretability. CAP provides a granular view of uncertainty across layers. Picture a dashboard where you can see which parts of the network are hesitant, e.g., early layers struggling with raw data, and which are confident, e.g., later layers refining predictions. This isn't just academic, it's critical for safety-critical systems. Imagine an autonomous vehicle's AI flagging uncertainty in low-light conditions, or a diagnostic tool highlighting ambiguous patient data. Uncertainty isn't a flaw, it's a feature. And CAP is proving that by modeling it correctly, we can build AI that's not just smart, but aware. If you want to understand how the next generation of models will think, learn, and decide, this is the research to watch. Stay curious, and let's keep pushing the boundaries of what machines can know.